Okay, my name is Corbin Neely, and my research has been about real-time 3D fiducial marker tracking for use in arc radiotherapy. So, introduction: radiotherapy exists as a tool to treat cancer. Just so you know that. Whoop, wrong way. Tumours are 3D objects, and radiotherapy is developed into methods that deliver 3D dose distributions, like intensity modulated arc therapy, which you can see it comes from different angles. And then there's VMAT, which distributes the dose throughout an entire arc. To encapsulate radiotherapy, it's the pursuit to maximise dose to the cancer cells while sparing healthy tissue. The 3D dose distributions that they've created in these modern treatments have steep dose gradients outside, so when you have intra-treatment movement, so motion while the treatment's going on, then that tumour can get outside that therapeutic zone, and that can cause errors in the prescribed dose. So DNA damage is what it's all about. High energy photons, they indiscriminately do cause molecular damage. And 1 gray, which is a joule per kilogram, produces approximately 1,000 single-stranded breaks and 40 double-stranded breaks. Whereas the strands, I'm talking about the strands of the DNA molecule. The aim is to disable the mitotic events in tumour cell proliferation, so that we can stop cancer cells multiplying and eventually shrink as well. So with radiotherapy, there's 3 volume definitions. The GTV there is the gross tumour volume. That just sounds like what it is, the gross tumour. And the clinical volume accounts for little microscopic invasions of the tumour around there. And then the planning target volume is what my research is focused on, is margins that are added to account for patient setup errors and intra-treatment motion. So the aims of my research is to develop a tracking algorithm that performs stereoscopic reconstruction of fiducial markers 3D location and arc therapy. The algorithm must be capable of computational speeds that will actually give real-time information, otherwise it wouldn't be very helpful. And it needs to achieve localization accuracy that makes reductions in the PTV margins a plausible idea. So the linear accelerators that are used in radiotherapy, as you see here, have an orthogonal imaging setup. The yellow is the treatment beam, and the green is a kilovolt, so they're different energies. The treatment beam is megavolt energies, and the green beam is kilovolt energies. And the kilovolt one is imaged by an onboard imager, and the megavolt one is imaged by these things called an EPID, which is an electronic portal imaging device. And both constitute an array of pixels. And because we don't have actually access to the kilovolt images in the research I was doing, all my study is just using EPID images. So an EPID is a amorphous silicon array, 1024 by 768 pixels. High energy photons come in, eject electrons. These electrons cause scintillation events in the crystal, which emit visible light. It's captured by a photodiode. Each of these represent a pixel in the array, and these are read out by thin film transistors. And so a tracking algorithm obviously needs a frame of reference, so this is just the coordinate system that I've used, and that there references the isocenter, which is the mechanical centre that this will rotate about. And so any future references to a 3D localization, I'm talking about a localization in this frame of reference. And a couple of phantoms, there was 3 phantoms, but I'm just mentioning 2 here, were constructed. These are made of just polystyrene blocks with gold fiducial markers in them. These markers are about 5 millimeters in length and 1 millimeter diameter. And the purpose of them is that the images produced by an EPID, I'll go back here, images produced by these, because it's such high energy, Compton scattering dominates and they're very low in contrast, and they don't show soft tissue very well. And so fiducial markers can be used as surrogates for the actual target you're trying to aim for. And so this one here, you can see they're oriented approximately axially with the coordinate system, and this phantom 2 here is the clinically more significant one because they're randomized, just the orientation of them, and also that they approximately fit within the diameter of a prostate tumour. And so for image acquisition, the phantom is placed in the isocenter. The gantry is brought down to negative 179 degrees, where 0 is top dead centre there. And the gantry rotates about as the EPID, this flat panel here represents the EPID, that captures images at a frame rate of 7.5 frames per second. And because just the way that the interaction between the energy the treatment beam and the EPID characteristics, there's a banding artifact, and so to remove that banding artifact, we use 3-frame averaging. And so each image in the data sets that I use represent a 2-degree gantry rotation. So here's a little overview of the algorithm. I cannot go into it all right now because it's just quite complex and it'll take too long, but I'll briefly overview a few parts of it. It's an original algorithm that I developed in C++ for its computational efficiency. And so you can see here, I import the images, I set my regions of interest, I create a dynamic thresholding. So thresholding is basically where you got your image and you just, anything above the threshold turns into white, anything below the threshold value turns into a black pixel value. It's called binarization. And then I perform this connected components, I detect the endpoints, I check if they're valid endpoints, if not, I repeat a process that only iterates through once, that's all that's necessary. And when I find true features, I project these into 3D coordinates, and then I use a Kalman filter. And this process is applied to an orthogonal image pair. So the first part is that, because I was working with C++, and there are a few DICOM readers that can process these things, but it's a bit like, I call it like. So now that these regions of interest have been projected in, they are in the continuous metric, so they don't make sense to an image. We need to convert them into something that makes sense, which is rows and columns. And so the transformation is just that, using this scaling factor again. 1 over p is the pixel pitch, which was 0.392 millimeters, and that just made them reference rows and columns of the image. And so once I've set my regions of interest, I use a dynamic thresholding, which is, as I explained, what thresholding was. And so first of all, in each region of interest, I find the average pixel intensity. And then I find the pixel intensity within a fiducial marker, and I use these to binarize the ROI. And this is dynamically adjusted for every circumstance. It's not, arbitrary or anything. And so how I find a fiducial marker, the intensity value within a fiducial marker is, if you imagine this as a pixel intensity profile, here's the topography of a fiducial marker, and you're just basically looking for a derivative that has that consistency of a fiducial marker. And you have to do it in both UV directions. U and V refer to pixel coordinates, U across, V down, so that, because you don't know which way a fiducial marker is going to be oriented in the image space. And so after I've got my binarized region of interest, because you never know what you're going to end up with. You might have multiple markers within the image, or you might have some segmented background. So to further differentiate what these will entail, you apply connected component analysis, which basically turns it from black and white, binarized image, into black, and then shades of grey. You just give it each component gets its own label, and that helps for differentiation of what's within your ROI. Connected component labeling is basically, I use an 8 neighborhood association. It's just, if this value is white, which is 255 in a grayscale image, any pixel around this, if any of those are white, they are classed as being associated and called part of a connected component. And then you label any within the same component with the same pixel intensity value. And then I created an original, so this is an original idea of detecting endpoints. So once you have your pixels of interest, this is now operating on the component labeled binarized ROI. So it's technically not binarized because there's more than just two values. And you search these 16 pixels around the ROI, and you compare if they have a value, if any of these pixels have a value same as your pixel of interest, you give it a value 1, if not a 0. And from that, you create bit sets that encrypt the region around your pixel of interest. And from that you can distinguish what are endpoints and what are not, because you get multi-sequences, and also sequences that are too long would represent non-detections. Endpoints have these kind of consistencies. And through that, you can equate an orientation angle. So now we've got a possible candidate of an endpoint. It can assign it an orientation, so it says that, hey, I was an endpoint here, and the fiducial marker was lying approximately this way. It's a quantized angle, it's not very accurate, and it doesn't need to be at this point in time. So, detected endpoints must possess qualities consistent with the geometry of fiducial, so must have approximately opposite angles, separation distance, ds, and also the pixel label, so it must belong to the same component. So now that we have endpoints candidates detected, they are in that discrete pixel coordinates, and so we need to transform them into subpixel intensities. So if you imagine that these are the intensity values, you can see that this is full attenuation of the photon beam here. It will be coming in and hitting those, so you get full values, and these, it's only partial occlusion, so it'll be less. And with this data, you can apply interpolation and then an argmax evaluation of that. You could do that, but that would be like, whoops. Oh, what happened there? Sorry about that. So you could do, and the noise within medical images is Gaussian, but I developed my own little method to do this job because it's computationally quite expensive to perform interpolation there. And so my method was pretty accurate with the same evaluation as the Gaussian method, but it was 8,500 times faster, so that was good. But I haven't described that method here because it's just a little side issue. It's not what my research was about, but that's a good result in its own as well. And so once we have these endpoints, then this stereoscopic reconstruction can occur. You can see here that first of all we get the Y dash value uses the geometry of the LINAC, the SID, and both the X locations of marker in image 1 and image 2. So that's using the orthogonality of the two images, and from that you can reconstruct the X and Z, and then now it's got to be projected back from rotated gantry coordinates into the LINAC fixed patient coordinate, and that's just another rotation matrix. And so we have a set of endpoints now with subpixel accuracy, but these are influenced by noise. So the final stage in the process is applying a Kalman filter, and the Kalman filter basically just is a method to describe the underlying state of the system when you have noisy data. As you can see here, this blue is a noisy signal, and red describes the underlying state of the system, because my data was noisy, because that's inherently the way you can get data from a medical image. And so here you can see that it uses the current state of the system and the past state of the system with a noise equation. And so all my results were Kalman filtered. And so one of the phantoms I didn't mention, we constructed a phantom that we independently measured with an optical comparator, so we could have form a ground truth. And so each point on these plots here represent the algorithm output, and then the measured output from the optical comparator, and then the difference between those. So you can see that we're talking about there, that's 0.15 of a millimetre. And so this is for, I was tracking 4 fiducial markers, and around as the gantry rotates, you can see that. And this is the typical kind of convergence that you'll see when the Kalman filter is building up its accurate description of the noise covariance matrix. You can see very little deviation there. And so that established a ground truth, so we could say that there was this method that was precise. And so that produced a root mean square error of 0.17 approximately. And oh, by the way, all the detections to reconstruct the 3D locations of 4 markers took about 20 milliseconds. So it was very fast. And so for Phantom 2, that was the clinically more significant one. I had more results, but I'm only showing a few here, because they're actually all pretty much the same. You just see the same pattern over and over. And so, yeah, for marker 1, marker 2, marker 3, marker 4, this time, because this is not independently measured, so this time each point is the average of all the data minus the location of that individual point. And again, you see very sub-millimetre differences. And so for Phantom 2, oh, by the way, there are actual error bars on here, because we did 3 separate runs of each experimental setup, so that we could evaluate not only was it accurate, but was it consistent in what it was outputting. And so the error bars are insignificant, you can't even see them on this sub-millimetre scale. And so each coordinate was analysed, but I only plotted 3D, because that sort of sums it up. And you can see the standard deviation, talking about very small results. Maximum error always occurs at the start of the plot as the convergence is happening. And the detection success of 94.6%. And then another imaging run of Phantom 2 with a bone surrogate, that was just aluminium placed within the image as to account for, because in a clinical situation you're going to have bones, and it's going to come up in the image And in a lot of other studies, that's proved a problem with the presence of bone within there. And it basically didn't change the results very much at all. And so the reason there's detection failures, and to differentiate, a detection failure does not imply a tracking failure. It will still perform tracking as long as there's not too many consecutive detection failures. Detection failures occur when you get markers cross each other's path, and then they later on project as the geometry of a fiducial marker. And also, sometimes there's bright regions that are just far too bright that you can't actually even see a fiducial marker. So it doesn't have a topography of a fiducial marker to find it. And so, if you recall, with the LINAC, there's that orthogonal setup, and the way that it is, we couldn't have access to the kilovolt imaging system. So, with the phantom that wasn't moving, there's a pseudo-synchronicity between the images. So, because it's invariant with time, you can therefore use images that are 90 degrees apart, and they still relate for stereoscopic reconstruction. But so, for a moving phantom, so this phantom it's just phantom 1 placed on another moving phantom that gives it a sinusoidal pattern. I performed 2D tracking just for proof of concept. So if I could track in 2 dimensions, I've showed that with stereoscopic reconstruction I can accurately depict the location in 3 dimensions. So if I can track in 2 dimensions, it adds a proof of concept. So that's what this is. You can see here, there's a large arc, and then you've got the 10 RPM sinusoidal, one for each marker. A large arc here indicates that it would be more off-centered, so this is due to gantry rotation, and the smaller one is from the moving phantom. So more off-centered, closer to the centre of the isocentric rotation. So that worked well, but you can't actually do any numerical analysis on that because you can't repeat the situation. So it gives you a sort of qualitative result. And that's the same for the V tracks of tracking that. And see if this works. I've got a little video. So this is the moving phantom. This is the sinusoidal pattern one. It's a bit hard to see, but each marker has been given its own, as was plotted. This one's red, that one's green, that one's can't quite tell, yellow. And this is the one I didn't do stereoscope because you don't have access to the synchronous images. But it still shows you can see that there's 2D tracking going on. And there's never a detection failure in this one because the image is so clean, because there's no treatment couch attenuation in there or bone, and so this actually has no detection failure. So that finishes there. And so the conclusion is the ability to track fiducial markers in arc radiotherapy using stereoscopic reconstruction can accurately account for target motion. Reduction in PTB margins used in all external beam radiotherapy treatment methods, in particular the complex ones of IMRT and VMAT, is therefore plausible. So, if there's any questions?